Hello and welcome to another EE140 video. Today's problem is on Faraday's law and Lenz's law. So let's begin. So we're given a thin copper wire that is oscillating on a conducting loop, and that oscillation is described by this function. We're also given a magnetic field that varies in time, given by this function. Now we are tasked to find the induced current on the loop and the direction of that induced current at time or t equals 0. We're also told that the equivalent resistance of the loop is just R. So first let's take a look at this function, the function for the oscillation, which is x of t equals x naught plus alpha sine omega t. So notice that in this function there's a sine in it, and sine functions are increasing functions. That's because from 0 will go up, go down, go up again. So at least for a few moments of time after t equals 0, sine is going to be increasing, and when you add that to x naught, you can determine that this function is an increasing function. Alright, now how about our function for B field? B sub t equals B naught minus beta t squared. So we can see that t is squared, and as t goes on from 0, this term is going to be bigger, and you minus that with B naught. So you can determine that this function is going to be a decreasing function. Also, let's take note that the initial B field is going into the page. So with that as our thumb, and the curl of our fingers is the current that comes with it, the initial current is going to be going clockwise. So we'll designate clockwise as positive direction. Alright? So with those in mind, we could now solve for our I induced. We could get started by obtaining our magnetic flux. Magnetic flux is just the amount of B field pouring into the closed loop, or this area over here. That could be obtained by integral B dot dA, and that is going to be the same as B A cosine theta, with theta being the angle between the magnetic field and the area vector of this loop, and they happen to coincide parallel. So the angle between parallel is just going to be 0, so cosine of 0 is just 1. So this term just becomes BA, which is just B field times the area of this loop. The area of this loop is just length times width. We'll let our x be our w, so that's going to be PLX. And we just plug in the functions while at the same time pulling out L, our constant. It's going to be B naught minus beta t squared times x naught plus alpha sine omega t. And that is our flux. Now that we have our flux, we could obtain our VEMF, or electromotive force. That could be obtained by this formula, d flux dt. And we'll apply our negative on the constant times the time derivative of these two functions. that is going to be, so we have to perform a product rule on this two, and product rule states that if we have two functions and that we need the derivative of those two, we could just do it such f prime of g plus g prime of f. So we'll let this term be our f and this term be g. That's going to be derivative of f is just negative 2 beta t times g x naught plus alpha sine omega t plus derivative of g. We have to perform chain rule, so let's write down our f p naught minus beta t squared. From inside, that's omega, and then the derivative of the outside is just going to be alpha cosine omega t so that is our VEMF. Now that we have our VEMF, we could calculate our I induced. That is just like in Ohm's law, volts on top, resistance bottom to obtain our current. That is just going to be your valve. X naught plus alpha sine omega t plus b naught minus beta t squared omega alpha cosine omega t all over R. Now that we have the magnitude, and this is in amps. Now that we have our magnitude for I induced, we just need to determine which of these two terms is going to be dominant when t equals 0, and that will in turn tell us the real direction of the induced current. So remember, this is from the B field. This term is from the B field. This term is from the area. Right? And from the beginning, we have these two. So if B field going into the page, it's decreasing. Lenz's law says that the system will have a B induced or induced B field that's going to be opposing the change. So if the B field initial is going into the page but decreasing, then the system will have a B induced coming into the page to prevent more decreasing of B field. And that B induced, if we let our thumb be our B induced going into the page, our I induced is going to be the curl of the fingers. So we determined that I induced will have a clockwise direction. So thumb into the page, curl fingers, that's clockwise. Right thumb, by the way. So that's going to be clockwise. Now for area increasing, remember from this term, again by Lenz's law, area increasing, therefore allowing more B field into the loop, so the system will counteract that and induce a B field, B induced, that is coming out of the page to oppose the change in flux. So again, with our V induced is our thumb, our I induced is going to be our curl of fingers. We stick our thumb coming out of the page and curl our fingers. That's going to be counterclockwise direction. So since over here we determined that by replacing t with 0, this whole function is going to be 0, while this is not, so non-zero. So therefore at t equals 0, the term for area is dominant. So therefore the direction of the induced current coming from the area increasing is going to be dominant. So this is going to win, and we'll have the direction of I induced as counterclockwise. So it's going here. Let me draw it a different color. It's going this way. And if it's going counterclockwise, that means the sign is going to be negative, because clockwise is positive. And we already see that there's already a negative sign over here. So that agrees with our findings. So I hope this problem is clear for you. Thank you for watching and have a great day.